Alright, so let's just start the lecture 2, the second part of the class. I'm going to talk about diffusion. I think S is missing here. The diffusion and the convection for this lecture right here. So the very first thing that I'm going to talk about is thermodynamic force. And I'm pretty sure you have never heard of these things in any other class. So let's just talk about that one. Previously, probably lecture 116, we defined the non-expansion work, right? Which was incorporated into mu, especially when you're talking about this electrochem stuff. Then that was in there, right? And for example, like with the cell wall, how many particles are actually moving from the one side to the other? That was the stuff that we talked about, right? That's got nothing to do with expansion work, but that was the work, right? So the cell wall here, and then that initially you had the two particles there, but by moving these particles on the other side of the cell wall, it sometimes cost more energies, right? So that was the non-expansion work. So basically we are observing how many particles are on the right hand side before, and then how many particles are on the left hand side before the reaction, and then we count the number of particles on the right hand side and left hand side after the reaction, and then just checking to see whether that number changed, right? But for this particular case, let's just not think about the system point of view, but let's just think of it the same thing with the particle point of view. So instead of counting the number of particles in the right hand side or the left hand side, we're going to be one of the particles. And then the work is, let me just try to erase this one. So this is like a particle stuff. Oops. So one particle, right? So going from the left hand side to right hand side, sometimes it might actually cost you some energies to go there, right? And there is a distance. So this distance is x, right? So going from here to there, this is before, this is after, right? So moving the particle from this position to that position is a work, right? So you actually get the chemical potential before the reaction, that's this position right here, and then after the reaction, it's just moving the particle from one place to the other, you get the chemical potential of that position right here, and then subtract, right? The final position minus initial positions. But the both cases that you're measuring the chemical potential on that particular positions, right? So the work, the dW, the non-expansion work, is equal to the changing chemical potential of the non-expansion work with this is the slope right here, the slope of the chemical potential multiplied by how much it moved, right? So let's just say that on the y-axis, maybe that initially it started out at this energies right here. That's your initial energies, right? And then that after the end, you had this chemical potential. The difference in chemical potential, which is that one, is equal to slope multiplied by the x, right? And that's the slope, that's the distance, right? That's the delta y right here. And Similarly, from the basic physics, the changing work or the work is equal to the force multiplied by the distance traveled. That's the basic definition of the work. So work is equal to force multiplied by the distance traveled. Okay? So that means that the force right here, because you see that the dx is here, the left hand side is the same, right? Then that one right there, that one has to be same as that guy, right? So that's what I have right here. The force has to be equal to negative of the d mu dx when the temperature and pressure being constant. And in part 1 of this class, we also found that the chemical potential of A, the liquid phase, is equal to the standard chemical potential, that's 1 atm and stuff like those, plus RT log of the concentration of A, right? You can find this one in the equilibrium constant for the liquid phase, right? Then if I actually have the aqueous solution with just a chemical A dissolved in there, then we can actually drop this subscript A because there is only one chemical in the aqueous solutions. Then that F is equal to minus d mu dx. Note that I don't have A here. At constant temperature pressure is equal to minus RT divided by C of that one. Now I should probably explain a little bit about this one. So if I actually try to do this integral right here, that's equal to log of x, right? So the 1 over x integrations becomes the log of x. Then the derivative of the log x has to be equal to 1 over x, right? So we take the derivative of that portion, so the derivative of that one, right? That's what we did right here. The derivative, taking the derivative of mu with respect to x, constant goes away, and then you have RT, you can actually make it front, and then you have log of C, right? The log of C derivative is going to be 1 over x, and then the chain rule is going to make the partial C over the partial x with a constant temperature pressure right here. And this expression right here, well, for this particular case, that one, they are called the thermodynamic force. Thermodynamic force. So it's gonna come out in probably the 3 weeks from now. That when we actually talk about the electrostatic interactions, it's gonna come out. So I just wanted to talk about that one a little bit here. And then also that we have a related stuff that's coming pretty soon. Alright, so let's do the diffusion. So consider the number of particles B passing the surface X. So we are trying to count the number of particles that's passing this surface right here. See that this surface right here, okay? And there is a two surface that's sandwiching this surface right here. And then if you think about this surface right here, it's positioned at x minus delta x, so that the delta x going that way, right? And then you actually think about this particle right here, the number of particles on that spot. You have the number of particles at x at the given time t minus that's a function of the x and t right here, right? minus the slope of n multiplied by the dx, or the distance x. So that portion right here represents the number of particles on this surface right here. And then of those, half of them is going to the right, half of them going to the left, right? Because there is no special directions here. So it's half of them going to the right and half of them going to the left, right? So you have this 2 here. And anything goes to the right, it's going to eventually pass these things right here. That just means that this surface right here is very close from that surface here. Okay? The same stuff here. We have this another surface on the right, so that it's positioned at x plus delta x. And then the number of particles on this particular surface is the starting number of particles plus the slope of that number functions multiplied by the displacement delta x. Notice that in this case it's going to be positive, right? And then on this spot right here, these are the number of particles on that surface, and then once again half of them is going to the right, which goes somewhere, and then half of them going backward to eventually go across these things right here, this surface right here, right? So we're going to be interested in that one right here, which is going to be the negative direction, right? Because x is reducing in that directions. So the number of particles that's passing through this surface in this direction right here is this things right here minus that one right here, right? It's the addition of these two things right here. That's going to give us a net flux. That's going to give us a net flux. Net flux really means that I have two things going backward. That means that I'm going to take one, then take 2 out of it. Then you have only 1 left. That's a net flux right here. And you can actually simplify this one. Nx and nx is going to cancel. And then that one and that one. One is going to be negative, the other one is going to be also negative. So it's going to be, you have half of that, half of that. So it's going to end up with this one right here. And the net particle flux. And by the way, that flux is the flow rate per unit area. The net particle flow per unit area per unit time. The rate is the per unit time, right? So, and we say that we actually do this experiment. Experimental measurement doing using the tau. Tau is a period. So the tau is the period of the particle actually moving from here to here, here to here, here to here. All of these particles going to the right is going to pass through these things, and then all of the particles on this surface going to the left is going to pass through these things. That's enough time to actually pass through all of those things. Those are the tau. Then the flux is equal to these things right here divided by the delta y, delta z. You know what the delta y and delta z is? The delta y is that one. That's your delta y, and that's delta z. So basically that's area right here. So this corresponds to the area per unit area per unit time, right? Because the tau is the experimental time that you spent to observe these things right here. And if I actually choose the x, delta x, this distance right here, and that distance, the delta y and delta z to be all the same, that's L value, then that L divided by L divided by L, right? So it's going to be 1 over L tau, these things right here. That's your flux. Don't worry, I'm gonna repeat once again. That's pretty much the same stuff, but slightly different, and it's a little bit more useful. Alright, so the same argument, I'm gonna repeat exactly the same argument, but I'm gonna multiply these equations by V divided by V, the volume divided by volume, which is equal to 1. So I can actually multiply, right? Because anything multiplied by 1 is not going to change anything. So what did I do? I just divide everything on top by volume and then multiply volume. Divide everything by volume, multiply by the volume. So everything divided by volume, multiply by volume. Everything divided by volume, multiply by volume. Now, N divided by V, that's concentration, right? So we're going to replace everything by the concentration. You get these guys. And then you add those things up, you get these things right here. And then same argument, what's the concentration flux? It's actually the number of particles going through that stuff, right? Because we didn't change anything right here. The same argument, the number of particle concentration flux is pretty much the same as the number flux, but divided by volume, multiplied by volume, right? So J unchanged. This is the number flux, right? Multiplied by the delta x, that's coming from this guy, and then divided by unit area, the experimental time, right? So once again, I'm gonna take the delta x, delta y, delta z to be L, and then what's the volume? Volume is equal to L cubed right here. So we have L cubed, L, L, L. Then you're going to end up with this formula right here. So instead of the number, we actually have the concentrations. And then we actually say that these things right here, the one that's in here, I'm just trying to change the color right here, that things right here to be D. That's a diffusion constant. Then we get the, one of the important equation that's called Fick's Law of Diffusions. That's flux is equal to minus d dc over dx. Alright. But we can do a little bit more on this one. Again, that J is equal to number of particle going through that surface divided by the area and the unit time, right? So that you're gonna divide everything by A and then delta T, right? So what's N? N is the concentration times these things. What's this? It's the velocity, the speed, multiplied by delta T. That's the distance traveled in the x direction. So that's the delta x, right? And then area is the delta y, delta z, right? So that's a volume right here. So what's concentration multiplied by the volume? That's going to be just a number, right? So we didn't change anything here. So going from here to here, it's no problem there because we didn't change anything. And then now that the delta t cancels, that A and A cancels, then we actually have this J has to be equal to the concentration times the speed, or the velocities here. Then what's what can I do about this particular equations right here? Let's just solve for the B right here. B is equal to J over C, right? Coming from this equation right here, right? And then what was J from the previous one? We had these things, right? So we're gonna put that things here. Then you get these things right here. Now let's go back to the thermodynamic force that we did in this beginning right here. We had this relationship right here. So this partial derivative of the dc dx, right? So the partial c over partial x of the Tp is equal to F multiplied by C divided by RT minus, right? Okay, so what was the thing? So you get these things right here. The C cancelled, of course. Then you get these things right here. So the velocities, the speed, is equal to these things right here. So we have this B equal to dF over RT, right? But what's this F that's acting on the particle right here? That's the friction, right? And friction is given by the F multiplied by the speed right here. So the F is the friction coefficient is given by this 6 pi 8 r. I don't remember what this thing is called, but this is called the Stokes formulations. This is for the spherical particle. That's how much of the friction that you actually get. That depends on the speed. So the friction force is given by these things right here, multiplied by the velocities here. So, but anyway, we're gonna use that one right here, right? So F is equal to the little f nu. So that nu can be equal to F over F, right? And that's also equal to dF over RT. So F is gonna be gone. And then you can actually multiply both sides by RT. Then D is equal to RT over F. Also D equal per particle base. This is remember that R is for the mode of the things, right? So the per particle base or the per molecule base, the diffusion constant, you can actually use these equations to actually get the diffusion constant. That's called Stokes-Einstein equations. I think it's called Stokes or the Stokes. I don't remember. Maybe maybe there was a S here. Well, maybe I shouldn't say that one. You can actually Google it. So that's probably good enough for the diffusion portions. Now let's do the convections. The convection is that the bulk of the fluid is actually moving, and then that particles are on it, right? So what's the flux coming out of that one? So we're gonna use this one right here. The J is equal to concentration times the velocities. So the J is the flux, right? The flux of the particle that's passing through this surface right here. So let's just think of this surface being the infinitesimally thin volume right here, then the inside of this thin volume, or the thin wall right here, inside of that, there is a starting concentrations, right? So let me just try to get a picture right here. So instead of the wall, let me just try to give a little bit of the thickness there. Then you're interested in the concentration inside of these things right here, right? And then you can actually get the flux on this surface right here, and then you can also get the flux on that surface too. So the flux on the left hand side surface, and then the flux on the right hand side surface, right? And those difference determines the concentration inside, right? If what's coming out of this surface is bigger than what's coming in, the concentration is going to decrease, right? And then if what's coming in is larger than what's coming out, the concentration is going to increase, right? So, and if the difference is really large, then that concentration is going to decrease or increase quickly, right? So there's a changing concentration with respect to time is equal to the flux difference between those two surfaces, right? That's pretty much what I have here. And if I actually make the wall as close as possible, like close to each other, then that it's thin enough that I can actually use this as a derivative, which is dj dx, right? But j is equal to cb, the c times velocities, and the velocity being constant, it's not going to change the speed of the flow on the left hand side of the surface or the right hand side of the surface because it's thin enough. Then you actually get this formula right here. Instead of j, you have the cv, but b being constant, it's going to come out this way. So that's pretty much what we have here. Alright, let me just talk a little bit more about this formula right here. There are some of the stuff that I completely forgot to explain that one. Is thinking about the unit here. So let me just write this one right here. So it's important to think about what is the flux here. We talk about this concentration flow per unit area, unit time. That was same thing as the number of particles per unit area, unit time, right? That's just because it was just divided by b multiplied by b, right? The volume. So that was same as that thing right here. So if I write something that j have a unit of the number per unit area, unit time, right? So that's pretty much what it's supposed to look like, right? But if I actually have these things divided by the delta x, what I actually have, I actually have the number divided by volume, right? Because n divided by a divided by delta x, right? So a multiplied by delta x is going to be the volume, right? And then I still have these tau things right here. Right? So it's the concentration. If I actually put these things together, this becomes the concentration divided by time, right? So we're gonna have exactly the same unit right here. So as I actually make the distance x to be smaller and smaller, right? Then what's gonna happen is that the time that's travel, it's gonna be shorter and shorter too. So that the partial derivative with respect to time is gonna be same as the partial derivative of the concentration with respect to the x, it's gonna be pretty much the same stuff too. If I actually replace this J by the CV and then the B being constant. I shouldn't say that constant, but it's that change in velocity is negligible along the two surfaces. Now, that's the convection part. And for the static fluid, the fluid not moving, we actually had a fixed law, right? Which was I didn't do that. Okay. Alright, for the fixed law, we actually have this could actually diffuse out in that way or this way, right? So instead of having this J right here, we're gonna plug in the J coming from that guy right here. So we're gonna substitute the J with this formula right here. Then what happens is that you get these things right here, right? Because that J is equal to, I think that was a minus D, right? I can't remember the sign. Minus D dc dx. Minus D dc dx, right? So we're gonna put that things into here. Then you're taking the derivative of C with respect to x twice, right? So you get these things. Minus and minus is going to cancel out. You get this one. So that's the diffusion part. And then if you add that portion right here and then that portion right here, you get the generic equations or the generalized diffusion equations, which have the diffusion term and then the convection terms. That's, if you add those things together, you have the concentration change on that particular positions. And of course, when you actually try to solve this equation right here, then that's more or less like a computerized the numerical solutions. Most of the times, the engineering people actually work on these type of things quite a bit. And I'm going to actually talk about only the easy solutions when the speed of the fluid is 0. If that's the case, you actually have these solutions. For the 1D case, this equation right here, if you put these things into the C in here, then left hand side is equal to right hand side. And for the 3D case, you have that things right here. Note that these things right here, it's just if there is no XYZ special directions, then this is just the cube of that one right here. Or maybe that start from here, it's the cube root is actually equal to these things right here. Alright, then I think it's probably a good enough for you to actually start these problems. So this is going to be your Excel project. I actually have another problem for this one right here. So please take a look at the blackboard to actually see all the problems.